Hi there. I'm happy to be in this slightly unstandard FC conference, and I'm happy to tell you a bit about our work together with Team Roughgarden. So I will say that I learned a bit about video editing for this unstandard conference, and I do hope that you will learn about mining pools from this talk. Let's have a short intro to mining. Miners take data, they add to it a nonce, and then they send it to a hash function. Now, the result of the hash function will determine if this indeed a valid block with this nonce. For the block to be considered valid, we will say that it needs at least 75 leading zeros. To be more exact, in Bitcoin, we're not actually looking at the number of leading zeros, but we just have some threshold and we need the result to be under it. But for the sake of conversation, we will keep talking about the number of leading zeros. Now, if the nonce did not result with enough zeros after hashing it, this means we need to guess again. So the miner will guess a new nonce. And here I will say that we're assuming that there's just a random oracle that they tap into and get a random number. Again, put it into a hash function and then see the number of zeros they got. Now, if there are indeed enough zeros, this block, together with the nonce, can be sent to the blockchain and the miner gets a block reward. Now, guessing the nonce and hashing and guessing the nonce and hashing, that is a process that can take a very long time, especially for a small miner with not a lot of computing power. So a small miner might wait a week, a month, until they find even single block. So to have a steady cash flow and to avoid this variance in the income, the miners can join forces and create mining pools. So the agenda for the talk today is the following. First of all, we will talk about mining pools in general. Then we will talk about reward sharing schemes, that is the theoretical base on which we will build our study of reward sharing schemes in mining pools. Then we will talk about ignoring the extra information. So we will show two theorems that what they say in heart is that yes, miners can provide extra information to the mining pool, but if we're aiming to minimize the variance, this extra information should be ignored. Finally, we will use these theorems to show that PPS is optimal variance-wise for all of the miners, be they big or small. Okay, so let's jump in and talk about mining pools. So in a mining pool, as we said earlier, miners join forces and they mine together, they find the block, and then they want to share the reward that they found. So the first question is, how do miners prove that they even worked on a block if they didn't find one in the end? So the way to do that is by sending shares. Miners send a share, which is the block with a nonce, that results after hashing with, let's say, 65 leading zeros. So 75 leading zeros is a valid block. So 65 is just a proof that indeed the miner was trying to find a block. Now, an interesting question is, okay, so we have the miners, they were mining, they proved to us that indeed they were working on finding the block. How are we going to distribute the reward between them? So a few standard ways are the following. Pay per share, or PPS, just means that once a miner finds a share that is a block with a nonce that result in a hash with at least 65 zeros, they send it to the pool and they get a fixed reward. As simple as that. A more sophisticated, in some sense, way is pay per last n shares. So in this case, once a block is found, we look n shares back and split the reward between the last n shares before the block. From the miner's point of view, they send a share, and then depending on the number of blocks that are going to be found within the next n blocks, this is the reward that they're getting. Another reward sharing scheme is the proportional reward sharing scheme. In this scheme, we just look at all the shares sent between two blocks, and every miner gets the proportional number of shares that they've sent between the blocks. So these are three examples. There are, of course, many more, but we will work with that. So now that we're talking about reward sharing in the mining pool, we see that there are various options, and we want to make a decision about what would be the best way to share the reward. Now, the one thing to remember is that the reason for a mining pool is to minimize the variance. Because if we only care about expectation, we don't even need to join a mining pool. We can mine by ourselves, find the blocks whenever we find them, and live our lives. The reason that somebody joined a mining pool is to minimize the variance and have a more steady cash flow. So in this in mind, we have two design choices to make. First of all, what information from the miners do we want to use? So, okay, so 75 zeros means a block. And maybe we set a share every time we find 55 zeros. But what about 65 zeros? Maybe we should give a bonus for that. And maybe the one miner that actually found a block, maybe they also deserve some kind of prize. Maybe by using this fine-grained information, we can reduce the variance. Another design choice that we need to make is how to determine the reward once we have the information. So we've seen this PPS, PPLNS, and others. Which one is going to minimize the variance for us? So before we jump into our results, let's quickly go over previous works. So a minor risk aversion was already studied using this utility function for a limited family of RSSs. Incentive aspects were generally studied in several papers. And another direction that people took is looking at the dynamics between several mining pools. Also, empirical studies were held, and they have shown that there is some centralization happening in mining pools. Also, an interesting consideration is the cost of the equipment. So when somebody joins a mining pool, this means that they went ahead and bought some mining equipment, and this can also affect the way that the dynamics in the pool happen. And finally, we will mention the axiomatic approach towards reward sharing study that was also studied. So now we can jump ahead and talk about our model. So let's give a few preliminaries. The miners are just set 1 to k, and we have a hash rate vector h1 to hk, where miner I has hash rate hi. We also have a set M of possible messages that would be accepted by the pool. So for example, all of the block plus nonce that result in a hash with at least 65 leading zeros. So now we can see that every share that a miner sends is of the form S, which is the sender, and M, the message that the sender found. So we will be assuming that the hash rate altogether sum up to 1, and this allows us to think about H as a hash rate distribution. When we think about a sample of a share, we can generate it just by sampling S by the probability distribution H, and the message just chosen uniformly at random from the message space M. With these preliminaries, we can go ahead and talk about reward sharing schemes. So a reward sharing scheme, or an RSS, is a random function that takes a sequence of shares and returns a real valued number, which is the reward that the last sender of a share is getting. So notice that phi can also be random. For example, in PPS, the RSS is just you get a sequence of shares, you only look at the last one and give the last one some fixed award. In PPLNS, again, we get a sequence of shares, we're looking only at the last one, and then for the last one, we give some fixed reward times a random variable, which is distributed binomially. And the way to understand this random variable is just that from the moment we got the share, we're going to hold n experiments, which are just, is this share a block or not? So depending on the number of blocks found in the next n shares, this is the reward that we get for PPLNS. We also say that an RSS is unbiased if in the long term the overall reward is proportional to the hash rate controlled by the miner. We will also want sometimes to only look at a specific miner j. And then we will think about the function phi of j, which is 0 if the last sender of a share is not j, and is just phi if the last sender was indeed j. Good. So now we have the basics and we can get some intuition. So in the graph that you see before you, we're studying the PPS RSS, where we're looking at the variance that the miner experiences as a function of the proportion of the hash rate that they hold. The red line shows the case of a single class, as it is in the classical PPS. You found a share, you get a reward. The green and blue one are the case where there are two classes of shares, let's say 65 zeros and 70 zeros. So we assume that you get some extra prize if your share doesn't have only 65 zeros, but 70. And P is just the probability that if a share is in the first class, it's also in the second class. And you can see that if the probability is half or if the probability is quarter, the variance is only growing. So here from these three options, we see that the best thing to do is just have simple single class and not use the extra information. So to prove the theorems, we need the concept of symmetrization. For an RSS phi, we define its symmetrization by taking the expectation over all of the messages that the senders could have sent. So the senders are staying the same, S1, S2, so on, but the messages, we're just choosing them uniformly at random, and we're taking the expectation, and this is phi, the symmetric version, the symmetricized version of the RSS phi. We call an RSS message independent, well, if it's independent of the messages. That is, if we don't use the information in M1 to MT. Notice that the symmetrization of an RSS is message independent. Good. So now we can say that symmetrization minimizes the variance. In the following theorem, we show that for every unbiased RSS, no matter what's the hash rate distribution, and no matter what is the length of the shares sent to it, for a minor j, the variance of phi j is at least as large as the variance of the symmetrization. So, in other words, symmetrization decreases the variance for every minor. And a direct conclusion from this is that the reward should be based only on whether the message that was sent is valid. We don't want to use any additional information when we're determining the reward. And indeed, message independence is very common practice in mining pools. Now, it might seem that theorem 1 hints at PPS being optimal. But remember that as in RSS, we're also allowed to add some randomness to the share that we received. So we will need some extra work to prove that PPS is indeed the best. But before we continue to this, we will take a second and prove theorem 1 because the proof is short and very nice. In the heart of the proof, we have the law of total variance. So, first of all, we note that if the last sender is not the minor j, then phi of j is just 0. So the theorem is true trivially. And now we need to assume that the last sender is indeed j and study this case. So let's look at the vector of senders and the vector of messages that they have indeed sent. Remember that the definition of the symmetrization of phi is just taking the expectation over all of the messages. So plugging it into the law of total variance, we get this. We need to remember that variance is always non-negative. This means that the right summand on the right-hand side is always positive. This means that the variance of phi j is at least as large as the variance of the symmetrized phi of j, and this ends the proof. So now we can talk about the extra work that is needed to prove that PPS is indeed variance optimal. For this, we have theorem 2, which we will not prove here, but you're welcome to look at the paper. And the theorem states that for every hash rate distribution H, again, any length of sequence of messages sent, for minor j, the PPS RSS minimizes its variance over all unbiased RSSs for the minor j. A direct corollary from theorem 2 is that for every hash rate distribution and sequence of messages, PPS simultaneously minimizes the variance for all of the minors. So before knowing this corollary and theorem, we might have thought that there is no RSS that is optimal for all of the minors, no matter the hash rate distribution. Maybe big minors would prefer one RSS, small minors would prefer a different one. But here we show that PPS is good for everybody simultaneously. And it's great that something like this even exists. And we will also note that the corollary holds also even if each minor chooses their own difficulty. So maybe a small minor would like to send a share already when they find something with 55 leading zeros. And a big miner doesn't want to bother, and they will send only when they find something with 65 leading zero. This is absolutely okay, and still PPS is going to be variance optimal. Of course, the reward will need to be proportional to the number of leading zeros each miner chose to send. Now, a problem with PPS is that the pool might run into deficit because the pool must send a reward immediately when a share is found. And maybe there is some bad luck, and for a while, no blocks were found, and now the pool has to pay more reward than it actually has. So there are a few solutions for non-deficit reward sharing schemes, among them PPLNS, proportional, double geometric, and others. And we can show, again, using the tools that we have from earlier, is that if we're looking at non-deficit RSSs together with three other very natural restrictions, PPLNS is the one that is variance optimal. And the proof of theorem 3 is a direct consequence of theorem 2. So in this work, we chose a tunnel vision to focus on variance minimization. This keeps our theorems and model simple, tractable. But another thing about this is that these results can be used if we add further considerations. For example, if we care about deficit, or maybe some other reasons that the pool would choose to behave differently. There are still many interesting questions to study about mining pools, and we believe that the theorems and the tools that we have shown in our paper could be very useful. So thank you for your time, and please feel free to write to us if you have any other questions.